So with nails, dozen was a convenient number, but a dozen is way too small to use with atoms. And so we're going to use a much larger number. And we call this the chemist's dozen. It's a mole. So mole, here we go. Come on, here we go. So that's not mole, a sauce. It's not mole, a small, furry, short-sighted animal that burrows underground. Okay? And it's not a black spot on your face. It's a chemist's unit. So when you hear the word mole, think funny dozen. Okay? It's like a dozen. It's just a counting unit. We have other counting units. Do you know what a gross is? Not something that is gross, but a gross of something. It's a dozen, 144. Do you know what a ream is? A ream of paper? It's 500 pieces of paper. So we have some other units like that we use. They just represent a particular number of things. The word mole is a short word, and yet it has an abbreviation, MOL. Don't ask me why, I think it's dumb. But here we go. 1 mole, 1 chemist's dozen, is 6.022 times 10 to the 23rd things. Okay? That's really, really big, right? That's a 6 with 23 zeros after it. That's what a mole is. And a mole is really, really important. This is one of the really important concepts of chemistry. And it also is something that confuses a lot of students. And I'll find, weeks later that some of you are like, I'm still not really sure what that whole mole thing is. It's a dozen. But instead of 12, it's 6 times 10 to the 23rd. It's just a crazy big number. And there is a reason for it being that number, but we don't care about that right now. It's just that number. So a dozen is 12. Why? Because it is. We've all agreed that a dozen is 12. A mole is this number. Why? Because the scientists decided that that's what it was going to be. That number is called Avogadro's number, and it's named after the guy who did a lot of experiments and made a bunch of discoveries that led to us figuring that number out. His name was Amadeo Avogadro. And he was actually born the year that our country was born, 1776, so that's kind of cool. So, mole, a mole of marbles. You could have a mole of marbles. 6.022 times 10 to the 23rd marbles. A mole of sand grains would be 6.022 times 10 to the 23rd sand grains. Gosh, I wish I could remember this one. Maybe it's on the slide. There's people have figured out a lot of cool if this then that things. Like I think it was if you had a mole of marbles, it would cover the United States to a depth of 8 miles or something. I mean, it's really crazy. I'll have to look some of those up and get them in the slides because I keep forgetting what they are. So here are 22 pennies, and these are the older pennies that are solid copper. So this many pennies would contain 1 mole of copper atoms, 6.02 times 10 to the 23rd copper atoms. If we had 2 large helium balloons, those would be 1 mole of helium atoms, 6.022 times 10 to the 23rd carbon atoms. The size of the mole, that number, Avogadro's number, is something that was determined empirically. That means by experiment. It's just a little problem here. I did all caps. I did small caps there, and that makes the G look wrong. So the numerical value of the mole is defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. That establishes a relationship between mass in grams and number of atoms, and it also, I'll leave that out for now. And so that allows us to count atoms by weighing them. If you don't remember this definition up here, I'm fine with that. The reason it is that way is because, I can't keep the same slide here going, that gives us a relationship between atomic mass units and grams that is really cool. Why carbon 12? Carbon 12 is very easy to obtain. It's very stable. And so they just kind of decided we're going to use carbon 12 as the standard. So I don't know if you remember, we defined the atomic mass unit as 1/12 the mass of a carbon 12 atom. And now we're saying that a mole is the number of particles in exactly 12 grams of carbon 12. And so that's going to establish a relationship between grams and atomic mass units that's very, very convenient. So let's do a couple of problems here. Let's practice converting moles to number of atoms. So convert 7.2 moles of neon to the number of neon atoms. So when you see mole, think, oh, that's like a dozen. And here I've given you that relationship just in case you've forgotten. And so we're just going to do this like it's dimensional analysis. And we're going to start out with 7.2 moles. And we're going to multiply by atoms and divide by moles because we want the units to cancel out. Then we have to ask ourselves, well, what's the relationship between atoms and moles? 1 mole is 6.022 times 10 to the 23rd atoms. And Avogadro's number requires you to use scientific notation on your calculator because you can't put it in there any other way. 7.2 times 6.022 E23 equals. And we get, this would have two significant figures, 4.3 times 10 to the 24th atoms. If you find yourself getting confused on problems like this, try doing something similar using dozen, because we're all real comfortable with dozens. So ask yourselves, well, if I had 7.2 dozen eggs, how many eggs would that be? Well, I would multiply by 12 eggs per dozen, right? And I would get 86.4 eggs. A calculation like that is easier for us to get our mind around, and easier as to check and see does the answer make sense. So like at Costco, you can buy 5 dozen eggs. This is 7.2 dozen. So it's going to be more than 5 dozen. Is that going to be a lot of eggs? That's going to be a lot of eggs. So is 86 eggs a reasonable number for 7 dozen? Yes, it is. If you got your numbers, if you got your conversion factor upside down, which is probably the most common mistake people make, and you came up with 0.6 eggs, is that reasonable? Less than 1 egg in 7 dozen eggs. No, that's wrong, right? When we're doing conversions between moles and number of atoms, if you end up with less than 1 atom, you did something wrong. Okay? You could have part of an egg, right? You could take an egg and break it and divide it up. You can't divide up an atom. Atoms are the smallest pieces that are that particular element. You can't just cut them in half. So we're always going to have more than 1 atom. So when you calculate the number of atoms in a certain number of moles, it should be a ginormous number. If it's a really, really tiny number, if you've got a negative exponent here, you've got something upside down. Convert 5.2 times 10 to the 25th platinum atoms to moles of platinum. Okay, so on this one, we're just going backwards from the one we did before. So 5.2 times 10 to the 25th atoms. And we want to know how many moles is that. It's like that many eggs, how many dozen? Well, dimensional analysis is your friend here. We want to multiply by moles and divide by atoms so that the units cancel out. And then, where does the 6.022 times 10 to the 23rd go? It goes with the atoms. Just like it's always 1 dozen equals 12 things, right? It's always 1 mole. My iPad is apparently exhausted as well. Times 10 to the 23rd. This is analogous to 1 dozen per 12 atoms. So when we do this, we have to be sure that we're entering scientific notation correctly on our calculators, otherwise you're going to get the wrong answer. 5.2 EE25 divided by 6.022 EE23 equals, and we get 86.4. Isn't that the number I got for the eggs? That's weird. It would be 86, yes. 5.2 has 2 sig figs, and so it should be 86 moles. Any questions? So I have to tell you a story here. So 10 to the 23. On 10/23, which is October 23rd, chemists celebrate Mole Day. Mole Day runs from 6.02 a.m. to 6.02 p.m. on October 23rd. So that's all very fun and everything. My husband is a chemist. I am a chemist. Our 4th son was born on Mole Day. It was just the most awesome thing ever. The only thing that would have been cooler is if he had been born at 6:02 a.m. or p.m. He was born at 8:30 p.m. because you just really can't control that too well. But he weighed 10 pounds, and he was 23.5 inches long. 10/23 on 10/23. We actually did discuss giving him the middle name Avogadro, but we decided against it. Because all the other children have Japanese middle names, so we decided we should stick with tradition on that one. But yeah, so Mole Day, he's my mole baby. Isn't that crazy? I mean, you couldn't even wish for that. So, a dozen nails, if you have a dozen big nails or a dozen small nails, are they going to weigh the same? No, they're not. Okay, so that's the point of the slide, but can anybody tell me what's wrong with this picture? I see things like this. One of them, there's not 12. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's great. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, I mean, this is just disturbing for a couple of reasons. Seriously, the point of your picture is a dozen nails, and you can't manage to get a dozen nails in the picture. What may be more is that. And yes, it bothers me. And so, here we go. Okay, so now, there we go, 12 nails. Yeah? Okay. So just like the weight of nails changes, even though you have the same number, the weight of 1 mole of atoms is also going to be different. So here we have a watch glass containing 1 mole of sulfur atoms. And I can't look at that and tell you if that's right. 6.022 times 10 to the 23rd sulfur atoms. Over here, we have a mole of copper atoms. same number of copper atoms, but this mole weighs 32 grams, this mole weighs 12 grams, just like the nails, because the individual atoms don't have the same mass. A sulfur atom and a carbon atom do not have the same mass, just like a large nail and a small nail don't have the same mass. So we have different kinds of masses. There's molar mass and atomic mass. We've talked about the atomic mass unit, AMU. It's 1/12 the mass of a carbon-12 atom. The molar mass is the mass of 1 mole. So that term, the mass, molar mass, means mass of a mole. At the end of chapter 5, we very briefly talked about formula mass. A formula mass is the mass of 1 formula unit. A molar mass is the mass of a mole. So a mass of 1 mole of atoms. Now, because of how the atomic mass unit and Avogadro's number were defined, the molar mass in grams is numerically equal to the atomic mass in atomic mass units. So this just becomes really convenient. So if we look up copper in the periodic table, underneath the symbol for copper, we see the number 63.55, or something close to that. What does that mean? That means that 1 atom of copper weighs 63.55 atomic mass units. But if we have a mole, a chemist's dozen of them, it weighs 63.55 grams. So all those numbers do double duty. They tell us the mass of 1 atom, using the unit atomic mass unit. They tell us the mass of 1 mole of atoms, using the unit grams. And so we say the molar mass of copper, the mass of 1 mole of copper, is 63.55 grams per mole. Each mole of copper weighs 63.55 grams. Any questions? So that molar mass is going to be different for different elements. 1 mole of sulfur is Avogadro's number of atoms. That is the same for everything, because a dozen donuts is 12 donuts, a dozen cars is 12 cars. Do they weigh the same amount? No, the cars weigh a lot more than the donuts. But 1 mole is always that number. But then over here, this is the mass of 1 mole. So 1 mole of sulfur is 32.07 grams. 1 mole of carbon is 12.01 grams. 1 mole of lithium is 6.94 grams. These numbers are on the periodic table. The lighter the atom, the less mass you have in 1 mole of that atom. And these guys right here are very useful conversion factors for counting by weighing. Because gram is something that we can measure on those balances over there. So we can measure out a gram of sulfur, and then we know the number of particles in that. So let's calculate the number of moles of calcium in 91.4 grams of calcium. So we've got 90, that's not a good color. That was the nail color. 91.4 grams of calcium. And we're trying to figure out how many moles of calcium. Do we know a relationship, or can we find one quickly that tells us how many grams is 1 mole of calcium? It's on the periodic table. 40.08. So we look on the periodic table. Sorry, I'm having troubles with my iPad here. And we see under, let's maybe draw this over here. So on the periodic table, the square for calcium looks like this. It's element number 20, its mass is 40.08. This tells us that 1 mole equals 40.08 grams. So we take our 91.4, grams of calcium. And we're going to divide by grams and multiply by moles. We're not going to remember, oh, you take the mass and divide by the molar mass or multiply by the molar mass. We're just going to look at the units. We're going to use dimensional analysis. So we put the units in there so the units cancel out. And then we stick the numbers in. It's always 1 mole is how many grams? 40.08 grams. So 91.4 divided by 40.08. And this should have 3 significant figures, so 2.28 moles of calcium. Any questions? Yeah, we can take a break. I was just thinking that myself. Okay, calculate the mass of aluminum in 6.73 moles of aluminum. So 6.73 moles of aluminum. And we want to know the number of grams, the mass. So we're going to multiply by grams and we're going to divide by moles. And we get the units to work out, and then when we ask ourselves about the numbers. Okay, so from now on, we pretty much have to have a periodic table with us at all times. Aluminum on the periodic table has got the number 26.98. That means that 1 mole weighs 26.98 grams. So 1 mole, 26.98 grams. So we've got 6.73 times 26.98. My calculator gives me a big old mess, but this is the end of our calculation. It should have 3 significant figures, and so I'm going to call it 182 grams of aluminum. Any questions? This is dimensional analysis with weird, funky units. That's all it is. We can also convert between grams and number of atoms, just like we did with counting nails by weighing them. So how many aluminum atoms in an aluminum can with a mass of 16.2 grams? 16.2 grams of aluminum. Now we can do this in 1 step or in 2 steps. We could go grams to moles to number of atoms. But let's think about this. What is the mass of 1 mole of aluminum? 26.98 grams. And how many atoms are in 1 mole of aluminum? 6.022 times 10 to the 23rd atoms. So 6.022 times 10 to the 23rd atoms weighs 26.98 grams. See that? 1 mole, this is the mass from the periodic table, and Avogadro's number. You can do this with any element. And so there's actually different things tied together here, 3 different things. And so, yes, we could go from grams to moles using Avogadro's number, and then go from moles to atoms using the molar mass. Or we could go directly from grams to atoms, because we know that 26.98 grams is equal to this many atoms. So that's the one I'm going to show you. 6.2 grams of aluminum. And I'm going to multiply by number of atoms and divide by grams. The mass of a mole is 26.98 grams for aluminum, and a mole is 6.022 times 10 to the 23rd atoms. Is this going to be a big number or a small number? It's going to be a really big number. And this should have, what, 3 sig figs, right? 3.62 times 10 to the 23rd atoms. That's an S, because I said it is. That wasn't any better. Any questions? We do the gram to mole calculations a lot. Calculating the number of atoms, this is a good thing to be able to know, to be able to do, but it's not as important as the grams to moles.